Hi, we're Project 12. This is Diamond Optics. My name is Todd Bean. I've got here with me Joe McCarthy and Josh Wilson. We are working on a test bench for Atomos Technologies, and we're sponsored by Dr. Marco Torelli.
Our sponsor, Atomos Nanotechnologies, is a material science company focused on operationalizing nanodiamond particles to produce an optical response when an external magnetic field is applied. Our sponsor tasked us with producing a test bench to modulate an oscillating magnetic field when applied over the sample of diamond dust. Some key requirements that our sponsor asked us to hit were the product must be reliable, easy to use, and produce accurate results.
So the way our project is impacting our sponsors is we're providing the test bench to a current optical test setup. And the way they're exciting this fluorescence from the nanodiamonds is they're providing a baseline optical source. That baseline optical source is then exciting the fluorescence from the test object. And then the modulated fluorescence is then modulating that optical response. So it's not a baseline DC, it's kind of oscillating up and down. And that oscillation can be fed into a photomultiplier tube. And all that does is it converts that optical signal to a voltage output. That voltage output has the same frequency as the fluorescence, which can be detected by a lock-in amplifier. And another important part of our project is we're providing that reference signal that's moving that oscillation up and down also to the lock-in amplifier. So we can use those two references and pull out the optical response for a cleaner picture of what's really happening.
For the design, we've got two housings. One of them has a permanent magnet which rotates on a servo. One of them has an electromagnet which is used to pick up objects usually, and we're oscillating that strength of that field to match our needs. Let's see here. And so if you look here, you can see the electromagnet is, we've turned it on, and we've got a signal here on the oscilloscope. The green signal is the on-off switch, essentially, of our electromagnet. The purple signal is the actual strength of that field that the sample is going to feel. So you can see that it rises up as in that short period of time. I think that's a 20% duty cycle. And then we kept it at that low level so that it could go all the way back down to zero. You can see from our diagram, the only connection really for the outside is the wall outlet and the lock-in amplifier frequency. That frequency, like Josh said, is passed in so that we have a reference for the signal, so that we can actually match up to what is being modulated by the magnetism instead of noise or something else. Then with the permanent magnet, it's a similar setup. We've got the signal from the Hall sensor, which is a sensor that measures magnetic modulation, being passed in to reference that frequency.
Feeding this signal, this yellow signal, to a lock-in amplifier, and that's providing this lock-in frequency. And kind of the key requirements for that lock-in frequency is it needs to go below 200 millivolts and then rise above it quickly. And then that peak threshold of 200 millivolts going up and down is how it kind of detects the frequency of the oscillation. So removing the DC portion of the Hall sensor is really important to make sure that the min value goes below 200 and the max goes above 200 to get that oscillation. And you can see that the oscillation of the Hall sensor and of the test sample space are the same.